Okay.
Thank you, Doctor.
No problem, anytime. So let's start. The first problem I want to solve is this one. Okay. So let's read the problem. So we have here a figure 12. So read the problem. Okay. So here I plot acceleration AX versus displacement X. Okay. For a particle that have a certain mass, and I give you the mass 2 kilograms. And the particle, which has a mass of 2 kilograms, is moving along the x-axis. So it's a one-dimensional motion. Okay. And then what I gave you here is acceleration versus position or displacement x. So here's a scale of the figure. On the vertical axis is set by AS is equal to 3. So basically this is 3. Of course, this is 2, and this is 1. And this is, of course, minus 3. The question is, how much work is done on the particle as it moves from x equal to, this is x initial, and to x final, 6 meters. So x initial is here 2, and x final is here equal to 6. Okay? So I want work. So here you see that the acceleration is a variable, it's not a constant acceleration. So the acceleration is variable. And you know that Newton's second law is telling you basically net force is just MA. Now, if I project along the one-dimensional axis here, I will have net force along X, which is Fx is just equal to MAX. Okay? So giving you acceleration versus displacement, I'm giving you force versus displacement. Okay? And what is the work? Of course, the acceleration is variable. That means the force is variable. We know that Fx is just MAX. Of course, AX is variable. That means the force is variable. What is the work of a variable force? Work of variable force is an integral between x initial and x final of Fx dx. Okay, so it will be integral between x initial, which is 2, x final, which is 6. Fx will be the mass multiplied by the acceleration multiplied by dx. So this will be mass, I will get it out. So mass is equal to 2 kilograms multiplied by integral between 2 and 6 of AX dx. And this is the area under the curve. Okay, area. So between, of course, 2 and 6, so I need to get this area here. It's a positive area. And I need to get this area, which is a negative area. I add everything, and that will give me the work of Fx. You know how to calculate an area, so I will not do it. So you calculate the work, and you'll find 12 joules. Okay, good. Now, what could I have asked? I could have asked another question. I could have given you V initial, meaning V at x initial, which is 2. So what is the velocity, the speed at x initial? I said it's equal to, let's say, 3 meters per second. Now I will ask you, what is V final? Meaning, what is the velocity at x final, which is 6? Yes, Mustafa.
Doctor.
Yes.
I know that the area under the curve is minus, but here, what does it mean with the work?
I will come to that. That's a very good question. Yes, that's a good question. I will come to that. Okay, so let's see here. Now my question is, my V initial is given 3 meters per second. Now I'm asking you, what is V final? Of course, you will use work kinetic energy theorem. Delta K is just equal to net work. Here, net work is work of a single force, which is work of Fx. And I already calculated it, it's equal to 12. Now, delta K will be half, basically K final, half mV final square. V final is V at 6. minus half mv initial square. I know m, I know v initial, I know the work, network. The only unknown will be v final, which is v6. Okay. Now, what Mustafa asked here, what does it mean? So here, of course, v final will be bigger than v initial because network is positive. Okay. Yes, that's obvious. Now, Mustafa, your question is, what does it mean? So here I gave you acceleration position graph. So basically I'm giving you acceleration is just f divided by m. Okay. I'm giving you f versus x. Okay. And of course it's a variable force. Now think about what does it mean? Here, if the area is positive, what does it mean? Here, of course, look at it. F is positive. Okay. But also the acceleration is positive and I'm moving in the positive direction. Okay. So I'm speeding up because I know that I'm speeding up. Why do I know I am speeding up? Because actually the work here is positive. And the displacement is positive, delta x is positive. And also F, which is A, is positive. Like in the first chapter or second chapter. Force and velocity have the same direction when I'm speeding up. Now, when I arrive here, acceleration is 0, and now the acceleration becomes negative. Acceleration become negative means force become negative, but I'm still moving in the positive direction. So velocity is positive, but acceleration is negative. I'm slowing down. And that makes sense because here the work is negative. So I'm taking work from the system. Okay. Okay. But overall, when I arrive here, still my velocity is bigger than here. Because the overall work, the network overall is positive. Okay. So here's this area, you will have a positive area and a negative area. And this is very good to ask yourself these type of questions. Yes, there is another question. Did I answer your question, Mustafa?
Yes, thank you, Doctor.
Now let's go to Abdullah. Yes.
Doctor, can you explain how V6 is greater than V2?
Okay. So I'm using work kinetic energy theorem. You know that work kinetic energy theorem is delta K, which is K final minus K initial is equal to network. Network is here. I already calculated it. It's plus 12. So that means K final is equal to K initial plus 12. K final is just half M V final square, which is V6 square. Because I'm adding a positive work. A network between these two is positive. Between 2 and 6 is positive. Okay?
Okay, thank you, Doctor.
Yes, yes. And these are, these are important questions, okay? And I'm happy that you are asking them because never underestimate a simple question. Okay, let me go to the next thing. So when you have this type of graph, ask yourself this simple question. Okay, what does it mean physically? Does it make sense with what I know from chapter 2? Okay. Okay. Does it make sense from what I know? Because we are looking at this thing, but in a different way. We can look at it kinematically, but here we are looking at it energetically. And of course, physics work and all the ways lead to Makkah. Okay, yes, I have other questions. So
yes, Doctor.
it's in Arabic, unfortunately.
Yes, my name is Hussein. So yeah.
Yes, go ahead, Hussein.
What does the slope represent, actually?
So who can tell me what is the slope of this slope here? I have an acceleration versus x. Now, what is the acceleration derivative of acceleration with respect to x?
Velocity.
No. You remember, we used to have acceleration versus time. Okay? And I told you the derivative of an acceleration versus time, that's called a jounce or a jerk. That's not in Physics 101. Okay?
Yes, I remember.
You remember that. Thank you very much. And acceleration is a slope of velocity time curve. But here I don't have time, I have x. So that's a very good question. Now, let's look at it this way. Let me, yes. Okay, this is a good question. And yes, this is what I expect from students. So here I have a versus x. So now he said, what is the derivative of a versus x? A, as I said, A is just what? A force. The coefficient of proportionality is a mass. Basically, this is derivative as a function of time of x of F divided by m. So basically, this is 1 divided by m, derivative of a force with respect to x. Now, what is the derivative of a force with respect to x? Who can tell me?
Work.
Think about it this way. No, it's not a work. Because you see, a force is a derivative of a potential energy with respect to position. Okay. Now, think about it this way. Spring force, F is equal to minus kx. What is the derivative of Fs with respect to x? Minus k. Okay. So this derivative here is a kind of modulus of elasticity. It's a kind of spring constant. Okay. It shows you how basically stiff is your system. Okay. It's proportional to the modulus of elasticity. Okay, that's out of the scope of Physics 101, but that's a good question. That's why I answered. Okay, now let's go to this problem here, which is, let's say, an A plus problem, or let's say BB plus. Okay, so let's read it carefully. We have a 25 kilogram block, M is equal to 25. And I give you the block is initially at rest. So V initially is 0. So this block is pulled across a horizontal rough surface. Of course, that means I have friction. That's why I give you the coefficient of kinetic friction, 0.3 mu k. Now the force which is pulling it has a magnitude of 80 in a direction of 30 degrees above the horizontal. The question is, what is the final speed, V final, of the block after it has moved a distance of 10 meters? Always, always, always in a dynamic problem, you sketch, okay? And you do a free body diagram. Let's say I started here from rest. I cover a distance here, okay? And this distance, this is a displacement d, and of course I know the magnitude of the displacement is 10 meters. The question is, what is a V final here? V initial is of course 0. This is my initial position. Let's say it's a 0. Now I will do a free body diagram. I am in dynamic. Always do a free body diagram. While you are doing this, you are figuring out the problem, okay? And you are seeing the tricks. Of course, I will have the weight downward. I will have the normal force upward. And I will have this force here, which is pulling my object. And it has a magnitude of 80 Newton. And this angle here is what? Theta of 30 degrees. And of course, I will have the coefficient, the kinetic friction opposing the motion. Okay. Did I forget a force? No. So you check carefully, okay? Of course, here V initial is 0, V final, I don't know. So here, I can solve this problem in different ways. The first way is using chapter 2 and chapter 5. So if I use chapter 5, I will just say net force is equal to MA. Now I will project along X, and I'll project along Y, and I will get AX, of course. I can get AX. Now AY will be 0, of course, because the net force along Y is 0. Okay? By the way, if net force along Y is 0, means plus Fn minus mg. Now I have to take into account this component, okay, of F, which is plus F sine theta, and this is equal to 0. That means Fn is just mg minus F sine theta, and theta is equal to 30. Okay, Now, just because the block is not accelerating up along the y direction, it's not jumping. Okay, so this is along y. Now along x, I can get the ax. Now, once I get ax, I will say, well, ax is a constant. So v final square is equal to v initial square plus 2axd. I know v initial, 0. I know d. I know ax. From Newton's second law, chapter 5, I can get v final. But this is a long way. Okay. And we are in chapter 7. I want you to use something else. Of course, I want you to use work kinetic energy theorem. So chapter 7, by the way, I can solve the same problem using chapter 8. Okay. Using conservation of mechanical energy. Delta K plus delta U G plus FKD is equal to work applied. And work applied here is work F. The work of this F here. Because that F is an external force applied to the object. But I will not use this. We will use this next week, next Thursday. I will just use chapter 7. So chapter 7, work kinetic energy theorem. Delta K is equal to net work. Delta K, of course, is K final, 1/2 of mv final square, minus K initial, which is 0. So now what is net work? Net work is the work of all external forces. So it will be work of gravitational force plus work of normal force plus work of frictional force plus work of F. So I have 1/2 of mv final square is equal. What is work of gravitational force?
0.
Thank you very much. Jazakallah khair. 0. Because gravitational force, of course, is perpendicular to the displacement. 0. What is the work of the normal force?
0.
0.
For the same reason. What is the work of frictional force? Minus FKD.
Yeah.
And what is the work of F?
Cosine F.
Yes. So
It's
it's
cosine.
F dot D. It's a dot product. So now it will be minus FKD. What is FK? You know that FK is mu K Fn. But Fn here is not equal to mg. Be careful. Fn is equal to what?
mg minus f theta, sine theta.
So it will be minus mu K mg minus f sine theta. If you forget the f sine theta, I forget your grade. Okay. Multiply by d. Now what is f dot d? Of course, the dot product fd cosine theta. This is equal to 1/2 of mv final square. I know everything here. The only unknown is just v final. And I get my answer, and it's A. Okay. So be careful here. Fn is different from mg. Of course, because I have another force which has a y component. Okay. Good. I will get the same answer if I use chapter 8, and I will get the same answer if I use chapter 2 and chapter 5. Now, I will give you something here. If I ask you the same problem, now instead of having F on top here, above the horizontal, F will be below the horizontal.
Change the minus.
Exactly. So here I will have a plus. Minus, so that means here I will have a plus. Basically, F now will be increasing the normal force. Okay. Now, let me say something very important, and I did not have time to say this in chapter 5. Now I can ask you a simple question. Which angle theta will give me maximum acceleration?
Zero.
No. Good try. That's a good guess, by the way. But That's not the right answer.
45.
45?
89.
60.
60. Why?
Because sine 60 is half. And yes,
You
60.
said 0, somebody said 60. No, you have to calculate it. And it will be tangent of 0.03 here. Okay. So what do you need to do is basically you need to do Newton's second law. When you do Newton's second law along the x-axis, let's do it. Along the x-axis here, I will have net force along x is equal to max. So that means ax is just 1 divided by m of net force. Now, what is the net force along x? Net force along x, I will have f cosine theta. What else do I have along x? I will have minus fk, but fk will be mu k fn. But now fn is equal to mg minus sine theta, minus f sine theta, sorry. So this is my acceleration along x. And you see this acceleration is a function of theta. Okay. Now, if I tell you what is the theta which will give you maximum acceleration, whenever you have maximum or minimum, basically, you need to calculate what is the derivative of x with respect to the variable, and the variable here is theta. When the derivative of ax with respect to theta is 0, that theta will give me the maximum acceleration. So here I will take the derivative of this ax as a function of theta. Of course, I will take out 1 over m. So basically I will have the derivative here. I will have 1. Derivative of cosine is minus sine. Okay. And I will have minus mu k. Of course, mg is a constant. And then I will have minus minus, it's plus. Right? So here I will have, what's the derivative of sine? Is cosine. And this should be 0. Bottom line, basically f is not 0. That means mu k should be equal to tangent theta. So the angle that will give you maximum acceleration is the angle which is tan inverse of mu k. Okay. So that now you take your calculator, what is the tan inverse of 0.3? So let me take my calculator. 16.6. Okay. So basically you calculate the acceleration, it's a variable of theta. You take the derivative of the acceleration with respect to theta. The theta that will fulfill that, let's say, condition will be the theta max. Okay. This is how you ask yourself problems. Okay. Don't just solve and halas, drink and eat and go to sleep. No, ask yourself extra problem. And I know that you are already doing that, but I'm just reminding you, because fazakir, as the Quran said. Okay, now let's go to the next problem here. Any question?
Yes, I have a question.
Please go ahead.
You take from the frictional force, the Fn, as mg minus f sine theta. Can you explain that? I didn't. Okay,
so this is because there is no acceleration along y.
Okay.
So net force along y is 0. Now, what is the net force along y? You look at all the forces that have components along y. So you will have plus Fn, because Fn is up, mg is down, so minus mg. And this Fy here is positive, plus Fy. But Fy is just F sine theta. And this is equal to May. Basically, this is equal to 0. So that means Fn will be mg minus F sine theta.
Oh, yeah. I get it.
Okay, now let's go to this problem here. I have many problems that I want to solve because I want to solve all of these problems. The rest, you have solutions, okay? I want you to solve everything, and then you can watch me solving, but that will not help you. Okay? What will help you is you try, and then you ask a question. You come to office hours. Oh, there is this trick. Why did we do this approximation? Why this is shorter than this? So let's look at this problem here. Again, this problem, I can solve it different ways. I can solve it using chapter 7, that I will do now. I can solve this problem using chapter 8. I can solve this problem using chapter 2 and chapter 5 plus chapter 6. Okay. And in each of these options, I have 1 or 2 ways to do it. Meaning, I can look at them individually, or I can look at them as a system. I can look at the whole as a system. Now, let's solve it. We're using chapter 7 and using the system. So, okay, let's read it first. So we have 2 masses, 2 kilogram mass. So let's say, let me call this one M1, and this one is M2, 3 kilogram mass. They are released from rest. Of course, V1 initial is 0, V initial is 0 here. Of course, V initial is 0, meaning kinetic energy initial is 0. So after the 3 kilogram mass has fallen by 1.5 meters, so basically this gentleman will fall down and be here, okay? And this, I will call it D, 1.5, of course, the distance. If this one fall down by 1.5, that means this one move to the right by the same distance, right? So the same distance here will be 1.5 meters. Meters, sorry. So after this has fallen down by this distance, 1.5 meters, it reached a speed of 3.8. So V final here will be 3.8 meters per second. What is a V of block 1? Final. Same. Why? Because I did not say it, but you know it. Of course, this rope is massless, unstretchable. Okay? As usual, the speed, or let's say the magnitude of the acceleration for this block is the same as the magnitude of acceleration of this block. The speed of this block is the same as the speed of this block because the string is unstretchable and it's not breaking down. Okay, now the question is how much work is done during this time interval by the frictional force on the 2 kilogram mass? Okay. So this 2 kilogram object is on this table here, which has friction, which is rough. So now the question is, what is the work of the friction here when this object moved on this table by 1.5 meters? I will use chapter 7. Okay. Now, before I use chapter 7, I am in a dynamic problem. What do? Free body diagram. Okay. Even if I can do it without free body diagram. So this 3 kilogram, of course, will have M2G. Here you will have tension, of course. Okay. And now here, of course, I will have tension here. And again, the tension here is the same as the tension here in magnitude, right? Because it's the same chord. Now here, of course, I will have frictional force, Fk. Of course, I will have gravitational force, M1G, and I will have normal force, but they are not participating in the motion here. Okay. So I have looked at the free body diagram of each of them individually. Now I will define my system. Here, of course, I will look at the total system. The total system will be M1 plus M2 plus the chord. Okay. Now I will apply work kinetic energy theorem to the total system. Delta K is equal to network. So delta K is, of course, K final minus K initial. Okay. Now what is my K final? K final is a final kinetic energy of my system. So it will be half M1 V final square plus half M2 V final square. Basically, this is half M1 plus M2 V final square. This is my final kinetic energy because the speed is the same for both of them. It's total mass multiplied by the speed square. Total mass of this system multiplied by the speed square. Now, of course, kinetic energy is 0, minus 0. And this is equal to what? Network. Now, what is a network applied on my system here? Now, of course, because I defined the system as this, now the tension is an internal force. Tension is an internal force. So he will not get into configuration here. I don't need to calculate the work of the tension. Okay. So network here will be work of what? Gravitational force. But I'm talking about this gravitational force. Let me call it M2G. Okay. And plus work of frictional force, plus work of Fn, which is 0, plus work of M1G, which is 0, because both of these two gentlemen, Fn and M1G, are perpendicular to the displacement. So what is the work of M2G? I'm going down, right? And the force is down, so it will be positive, plus M2GD. Okay. This 3 kilogram object is falling down by 1.5 meters. So what is the work of the gravitational force on this 3 kilogram? It will be M2GD, and it's a plus. Why plus? It's going down. Okay. Now, what is the work of friction? Well, the work of friction is what I want. Just work of friction. So I end up with work of friction is just half total mass V final square minus M2GD. You do the calculation and you'll find -8. Is it clear?
Yes.
Okay. Now, another way to do it, a longer way, is I can apply work kinetic energy theorem on M1, and I will apply work kinetic energy theorem for M2. And then I will have a system. Now, of course, I will have to take into account the work of the tension now. Because if I look at work kinetic energy theorem of M1, I will have delta K for M1 will be network on M1. So I will have half M1 V final square minus 0 is equal to network. Network here will be work of tension plus work of friction. Okay. Here the work of tension will be positive and the work of friction will be negative, of course. Now for M2, I will have half M2 V final square minus 0 is equal to what? Work of tension plus work of the gravitational force. Okay. Now, but here now, the work of the tension here will be positive or negative? For M.
It will be negative, right?
Yes,
No.
because it will be negative, yes. Why? Because it's slowing down the motion. You see, for M2, the tension here is doing a negative work. Because the tension is up, the displacement is down. So it will be negative. Okay, but you can solve it and you will get the same answer, by the way. Okay. You can also solve this problem using chapter 8. You can solve it using chapter 2, chapter 5, and chapter 6. Meaning finding the acceleration. You can find the acceleration if you want. Okay. Now, okay, how much? Oh, I just have 10 minutes left. Subhanallah. Okay, so let's look at this problem here. Inclined plane. So I have a 4 kilogram block which slides down 2 meters, okay, 2 meters down, a rough inclined plane. So always you sketch. So this 2 meters is basically this distance here. D is 2 meters, okay, from point A to point B. So point A is here, point B is down here. Okay. So I gave you this angle here, 30 degree. So in reality, I'm giving you also this height. Because you know that sine theta is just height divided by d. Okay? Meaning the height is just what? D sine theta. And this will come again and again and again. Now, on this object, I have a force of 3 Newton that act on the block. So this force here is up here. You can see it here. F has 3 Newton. Okay? Now I give you the kinetic energy at A, Now the question is, what is the kinetic energy at B? Okay. So you will use, of course, work kinetic energy theorem. Delta K is equal to network. Delta K will be K final, and K final is KB minus K initial, which is KA, is equal to network. Now network here, of course, I will have work of gravitational force plus work of frictional force plus work of F itself. Okay. So let's start first by the work of the gravitational force. I'm going down, and I told you the work of gravitational force just depend on the vertical displacement. So it's just plus or minus mgh, and here it will be plus, and h being d sine theta. So h will be just what? 2 sine 30 degree. So that's what I did here, okay? Wg, okay? M for g, and this is h. H is d sine theta. So I get the work of the gravitational force. Okay? Plus, because I'm going down. You can look at it now, you know that the work of gravitational force is just minus the change in gravitational potential energy. But that's in chapter 8, okay? But you know that physics works and all the ways lead to Makkah. Okay, now what is the work of F? Of course, the work of F will be minus Fd, sorry, okay? Because D is downward, F is opposite, so the angle between them is 180. So it will be just minus F 3 Newton multiplied by D, which is 2, and you get minus 6. And now what is the work of frictional force? Okay, it's just minus FKD. Now what is Fk? Fk is just mu k Fn, but Fn is not equal to mg. I'm on an inclined plane. Fn here is just mg cosine theta. Okay, so basically it's just because I don't have acceleration along y. So normal force is counterbalancing the y component of my gravitational force. Okay. And I get the work, of course it's negative. Now I can get the net work. I just sum all the different works. I know the initial kinetic energy. I know what is the final kinetic energy. And you see the final kinetic energy is bigger than the initial kinetic energy, meaning I'm speeding up. Okay. Okay. This force and the friction are not enough to, still the x component of the gravitational force, the mg sine theta, is dominating the motion. So I'm going down and I'm speeding up. Okay. You can solve the same problem using chapter 2 and chapter 5 and chapter 6. Okay. Is it clear?
Yes.
Now, how can I make it more difficult? How can I make it nasty?
Added horizontal force.
Yes, this force here, instead of the force being along the incline, I can put it up here. I give you the magnitude and I give you the angle. Or I can put it down here. Okay? And I ask you the same question. Anyway. Okay, let me erase this. By the way, do you think that I'm shouting? Because my wife told me that I am shouting at my students. I said, no, I'm a cool guy. I don't shout. Am I shouting?
No, teacher.
Yeah.
Good.
No.
No, doctor.
Yeah. Because I'm used to be in a big classroom with 90 students. You have to shout. But yeah.
Doctor.
Our computer.
Doctor.
Sorry?
Sorry for interrupting you. There are students who want to join the lesson.
Okay, let me see. He's not in the waiting room now. Yeah, so I don't know. Yeah, okay, tell him to try to get in and I will accept him. Okay.
Okay.
So, yes, so this is another problem, but let me think. Okay, I want to solve this problem as well. Okay, I will skip this one. Now let me go to this problem here. And then I want to solve this problem. Okay, let's see. So we have how many minutes left? Okay, 3 minutes left. Let me try to solve this problem. So here we have a car, and I give you the mass of the car. It accelerates uniformly, meaning the acceleration is constant. Now I start from rest, and I reach a speed of 108 kilometers per hour in 20 seconds. Okay. So here I have constant acceleration motion. Acceleration is constant. So the question is, first, what is the power delivered by the car engine at t equal 20 seconds? I want an instantaneous power, the power of the car at t equal 20 seconds. So you know that instantaneous power is derivative of work with respect to time. In other words, it's just F.v, sorry. It's a dot product between the force and the velocity. Okay. Now here I have to find the force first. I need to find, of course, the velocity at v at t equal 20 seconds is known. It's 108 kilometers per second. You put it in meters per second. Okay. Now, how to get the force? Well, you know that the force is ma. Okay. So the force is the mass of the car multiplied by the acceleration of the car. The mass of the car, I know it. The acceleration of the car, I can use the constant acceleration motion. V final is equal to V initial plus AT, and then I get the acceleration of the car. Okay. So now the power at t equal 20 seconds is just ma, which is my force, multiplied by my speed at t equal 20 seconds, and then I get the power at t equal 20 seconds. Now the second question is, what is the average power delivered by the car engine for a time interval t equals 0 to t equal 20 seconds? So average power is net work divided by time interval. Okay. By here, I mean, what I mean by network, of course, network is work of the engine here. Okay. Because the rest of the forces will have 0 work. Okay. Good. So network, how do I get it? I use work kinetic energy theorem. So work of the engine is equal to network because all the other forces have 0 work. You will have, of course, gravitational force, you will have normal force, but they are not working. So the network is the work of the engine. So it will be K final minus K initial. K initial is 0, K final, I know the mass, I know V final, I get it, and I get the average power. Okay, so it's time. This is also an extremely important problem. Solve it and understand it. Okay, solve this problem. This I gave it as a quiz a year ago. Okay, so solve these problems, all these problems. Okay, the spring. I will solve a problem about spring because I will come back to these problems. Okay, so please solve all of them, and I gave you the solutions. I made your life easy. Okay, so make good use of it. And inshallah, don't disappoint me in next midterm exam. I want everyone to get full mark. Okay, so let's stop here. Thank you very much. Have a good day. Oh, I forgot to take attendance. Subhanallah al-Azim. So let me take attendance and then inshallah see you on Thursday. So please somebody, can you share the link? And I will open the form in a second. So somebody share with us the link. Thank you, Hussein. Yes. Okay, so have a good day. Assalamu alaikum.